Hello everyone, welcome to our first online meetup this month, and I hope all of you are safe and well. And thank you very much for joining with us today. And let me introduce our special guest speaker today. He is Alex Casalboni. He is a developer advocate at Amazon Web Services. And thank you very much, Alex, for accepting our invitation. I think we can start now. Alex, let me hand it over to you.
Thank you very much. Here we go. Great. So thank you for inviting me. It's a pleasure. So this session is about cost and performance optimizations for AWS Lambda and serverless applications in general. And I'm a developer advocate with AWS. I'm from Italy, so hi from Italy. I come from the web world. I'm a software engineer. I've done some data science. I've done some startup experiences. And I also organize some conferences around the world called Serverless Days. This is the official T-shirt as well. And before doing this, I was an AWS customer myself. So feel free to reach out to ask me a question, technical or non-technical. You can find me on Twitter, LinkedIn, and so on. So what I like to share today, I'll go through some very quickly. I'll go through some fundamentals. I want to share some best practices, and here I say optimization. I'm not saying cost or performance, because what I think is very often with serverless applications, these two dimensions, cost and performance, can really align with each other. So you can solve both with one shot. And then I want to share an idea or a project, this idea of a data-driven approach to solving some of these problems. And I want to conclude with some real-world examples and some, let's say, a framework, a mental framework to think in terms of patterns like cost and performance patterns. After that, we should have enough time for some Q&A. So feel free to share your questions. If we don't have enough time, I'll be happy to take some more questions on social media. So very quickly, fundamentals. What are we talking about and what we are not talking about? Often people talk about serverless in a way that you can reduce costs by using serverless. Okay, that is true, but it's not the topic of this session. Today, I want to tell you how you can take a serverless application and optimize it for cost and performance. So I'm not going to talk about other computing platforms or approaches. This is how Werner Vogels, our CTO of Amazon.com, talks about serverless. So I really relate to this as a developer, because what we want to do as developers is focusing on what we call the business logic. What are we building? We're not working 8 hours a day to maintain a cluster. We're not working 10 hours a day to do some operating system patches. In my career, I've been working 8 hours a day and more to solve a problem, to build some application business logic that was then used by some customer, user, whoever wanted to use it. And we really want to focus on that. What do we mean? The thing is, that's maybe 50% of the equation, because after you have written your code and your application and your business logic, usually someone has to take it, deploy it somewhere, operate it in a production environment, monitor it, eventually fix a problem, and be woken up at 2 a.m. if there is a problem. So there is a lot that needs to happen after you write your code. And what serverless allows you to do as a developer is that you can also own that in addition to writing the code, because the platform takes care of most of the heavy lifting about configuring the cluster, patching the underlying operating system and the whole stack, all the networking. There is a lot of heavy lifting there that you don't have to take care of as a developer when you work with serverless. And serverless, in fact, is not just 1 or 0. Serverless is a kind of a shade of serverless. You have things here on the left that are totally not serverless, EC2 bare metal, or running MySQL on EC2, or doing stuff at the bare infrastructural level. That's very not serverless. And on the other side, you have things like Lambda and DynamoDB and S3 and EventBridge, SQS, SNS, or Athena, where you really cannot even see the servers. You cannot even see the cluster underneath. Of course, there is always a server somewhere, but it's not your responsibility, okay? In the shared responsibility model of the cloud, that's the vendors, that's AWS's responsibility. But then in between, you have things that are maybe 40% serverless or 70% serverless. If you look at Fargate, if you look at Aurora serverless, or if you look at Kinesis, things where you cannot access the cluster, but maybe you have to do some capacity planning anyway. With Kinesis streams, for example, you have to set up the number of shards. So that's not the number of servers, but it still kind of pushes you into doing capacity planning and understanding your architectural infrastructural requirements. That's many other services like SQS or S3 really don't kind of force you to do that. So it's a kind of a shade, it's kind of a spectrum. And well, today we focus mostly on the function as a service side, which is AWS Lambda itself. But keep in mind, it's not just Lambda, it's not just function as a service. This is what the interface of a Lambda function looks like. So you have this idea of a handler. This is in Python, but it's very similar in most other languages too, where this handler will take an event in input. Everything is event-driven. So your function is not just there running 24/7, waiting for something to happen. You just don't even pay for it when nothing is happening. So when your function is invoked, that's because some event triggered it, whether it's a new item on DynamoDB, or a new object on Amazon S3, or a new user in a Cognito user pool. You can plug your functions and connect it to events. And this is, I think, a great differentiator with respect to many other function as a service. It's great to have function as a service, but if you don't have a lot of built-in native cloud integrations with tens and tens of services, it kind of misses the point, in my opinion. So looking at the performance side, what needs to happen in order for your function to be executed? So first of all, we need to kind of grab your code from somewhere, and the way you do it is you upload your code to Amazon S3 as a zip file, as a deployment package. Once we have your code, we can actually start what we call a micro VM. This is open source technology called AWS Firecracker. This is the technology under the hood of Lambda and other serverless services in the platform. After that, we can bootstrap the runtime, depending on which programming language, which runtime you have chosen, whether it's Python or Node.js or Java or Go or Ruby or whatever else. If some of the runtimes are not natively supported, you can even provide your own custom runtime. So customers and partners have been developing custom runtimes for languages like PHP or Fortran, or I've heard of a customer running COBOL on AWS Lambda. So you can more or less run anything you want on AWS Lambda. After that, we can finally start your code. Okay, so your business logic, your handler. Now, all of this happens in a bunch of, let's say in a few hundred milliseconds. So it's not like spinning up an instance or spinning up a container. It doesn't take a minute. It doesn't take 30 seconds. It takes hundreds of milliseconds. So that's the crazy big difference here. And what happens, in the first three steps is what we call a cold start. Cold because this only happens if you haven't executed, if you haven't invoked your functions for a while, or in the moment where you are scaling horizontally, so that many concurrent executions are coming into the system, and we need to, kick off new runtimes for you. Now, there are things that AWS is doing every single day to minimize the impact of, this half, and also the managed runtimes, actually. But there are a lot of things that you as a developer, we as developers, can do to optimize our serverless application. So today we will focus on the second, okay? Just a reminder for everybody, in case you have used Lambda in the past, let's say last year, and you needed your functions to be in a VPC, and you were experiencing pretty long cold starts in the order of 10 or 15 or 20 seconds, now that totally disappeared. So if you haven't used Lambda in a while and you still need to access resources in a VPC, say Redis cluster or an RDS database, before it used to be tens of seconds, 10, 20. Now it's very, very close to all the other Lambda functions not in a VPC, so in the order of 100 of milliseconds. So pretty cool improvement. And this is available in every regions since November, December of 2019. So already more than 6 months. Just a reminder for everyone, because this was probably the biggest performance concern of customers that I've met in the last 2 years. Now, when it comes to optimization best practices, I like to categorize them into 2 different categories. First category is all those best practices that help you minimize the cold start effect. So let's start from there first. So there are a few things you can do to reduce the cold start effect, but keep in mind that usually in the average workload, cold starts are a very, very small percentage of your invocations. If your function is invoked a few times per minute, your cold start percentage might be, I don't know, 1% or even smaller. So if we want to optimize this part of the equation, it's because either we have a very large cold starts, because maybe we are using some heavy libraries, or because we have a very high throughput, very latency sensitive kind of workload where our end users will experience a worse user experience. Yeah. If we can shave off 100 or 200 milliseconds from the cold start, that would be great for the user experience. So there are cases where you still want to optimize for cold starts. Now, for example, we always suggest to minimize, to avoid the idea of monolithic functions. Monolithic meaning you put everything into a big fat Lambda function, all your routes, all your APIs, all your business logic. Maybe you do some routing inside the function. Now, this is not evil. This is not bad per se. It might not be optimal. It might not give you the flexibility, the granularity that you need at large scale. It's still fine in many scenarios, but as far as performance is concerned, it's definitely not optimal, because you end up with larger deployment packages. And as we saw earlier, if we have more bytes to transfer over the network, that means the cold start will be longer. So what you can do, basically everything you can do to minimize the deployment package size, that will help a lot. Then what you have inside the deployment package also has impact. All the code, all the dependencies, all the initialization stuff that you need to initialize in your code, that also has an impact. So something else you can do, well, minifying, uglifying still relates to the idea of minimizing the size, the total size of the package in bytes. But then, when you go and use and run the code, you can do things like optimizing dependencies, for example. I'll show you an example in a second, but in a few words, based on how you import some dependencies, for example, the AWS SDK, you might be able to shave off a lot of milliseconds by importing some sub-modules, for example. So instead of importing the whole thing, instead of importing the whole SDK, you can import a subsection of it, a sub-module of it, and that might help you reduce this initialization time. Another trick, another tip I want to give you is this idea of lazy initialization. So what happens is that many developers like to have in one single file a lot of functions, and that's fine. But what typically happens is that you have a lot of handlers, a lot of function in the file, and you put at the top of the file all your initialization code. Now, that's also fine, but if you think about it, if all these functions exactly reuse the same libraries, the same dependencies, the same common shared variables, that's fine. But very often, these different handlers will use different clients and different libraries and different packages that you are still initializing up there for all the initialization code of all the handlers in that file. So a very simple way to optimize that, either you split the file, so you have one function per file, one handler per file, or you do what we call lazy initialization. So you still define the shared objects, the shared clients, the shared whatever in the initialization part, but then you actually initialize it inside the handlers, maybe still using some shared functionality. I'll show you an example in a second. So let's go back to the idea of optimizing how you use dependencies. This is some data that one of the AWS heroes, Yan Chui, found. I think he published an article a few months ago, maybe last year, about how to efficiently use the AWS SDK for Node.js. So for example, instead of importing the whole AWS SDK, if all you need is the DynamoDB client, you can just require the Dynamo client directly. Now in Lambda, well, depending on how many gigabytes of RAM, how much memory you have, this might end up with a pretty large savings in terms of milliseconds. And milliseconds means performance, but also means cost, because you're not paying for those 125 milliseconds. The same happens for the X-Ray SDK. So instead of importing the whole thing, if all you need is the core, you can shave off another few 5, 6, 10 milliseconds. If you do both, you can get up to 140 milliseconds. Now, I think, yeah, there is an article from March last year where Jan is sharing a lot of statistics about different runtimes and different SDKs and different metrics. This might be already a good way to shave off a few milliseconds. Another way is this idea of lazy initialization. So let's imagine that I have two handlers in this file. In this case, I'm using Python, and I have an S3 client and a DynamoDB client. Then I have one function, one handler that only needs the S3 client, and another handler, another function that only needs the Dynamo client. Now, instead of initializing both of them up here, I can just define them as none or null in other languages, and then lazily initialize them inside the handler. So this object will still be reused across invocations, but you're not, summing up the initialization time across the different functions. Now, for an SDK client, the impact is nothing. Okay, probably under 1 millisecond. But if you have other objects, other libraries, other heavier dependencies, if you do that, you might end up optimizing some of these functions in the same file. Another tip I want to give you related to cold start optimization is a new feature. Was launched about 6 months ago. It's called provision concurrency for Lambda. So basically, there are many use cases where that you're going to have a peak. Let's say that every Friday at 8 p.m. I don't know, there is a match, or maybe you are a streaming platform, and that there will be a huge peak in traffic with your serverless application. And that was pretty tough of a problem to solve if you wanted to pre-warm a lot of Lambda runtimes. Let's say you had from 0 to 1,000 concurrent invocations kind of peak, predictable. So what you can do now is you can use provision concurrency and say, hey, I will need 1,000 warm runtimes at 8 a.m. So you don't actually say 8 a.m., but maybe at 7 p.m., you'll start provisioning because there is a ramp-up time of about 500 per minute. So if I need 1,000, it should take about a couple of minutes to ramp up. And after that, you have these 1,000 runtimes warm. So as long as you keep them warm. So if you end up with 1,000 concurrent executions from 0 to 1,000, no cold start at all. If you get 1,200 concurrent executions, well, 1,000 will be served by the warm runtimes, and then you will spin up 200 more runtimes in the typical pay-as-you-go regular execution mode. So very nice for specific use cases. I wouldn't recommend to keep it on 24/7, but if you have predictable peaks, it's a great way to solve that problem. Plus, it's already supported by CloudFormation, Terraform, Serverless framework, and a lot of the monitoring partners too, like Epsagon, Lumigo, Datadog, Tundra, and so on. So give it a try if you haven't yet. Let me know what you think. Now let's get into the second category of optimizations, where we want to actually optimize all the other executions that are not related to cold start. Now, as you will see, most of these techniques will kind of force you to re-architect the application or to change how you trigger events or to add an additional layer somewhere. Or, for example, the first one, externalize orchestration. Imagine that all you're doing in your function is start a task somewhere else in a service and then wait and poll for 30 seconds until the task is over. This kind of orchestration things, that's kind of expensive if you want to do it on Lambda, because you are paying for idle. You don't want to pay for idle. That's kind of the point of using Lambda. You want to be event-driven. So something you can do is externalize that orchestration part and maybe use an ad hoc service like AWS Step Functions. So Step Function also has a price, a pricing, some cost involved, but it's much more event-driven, and you're not paying for idle compute. If you need a waiting state for 10 minutes, wait for something to happen and then go to the next step, you're not paying for those 10 minutes, because in Step Functions, all you pay for, you build a state machine, and then you only pay based on how many state transitions you have in that state machine. So it can actually be much, much cheaper than doing a lot of polling and waiting and looping inside a Lambda function. Another tip for you is this idea of using Lambda functions to transform data instead of transporting data. So, for example, if you want to get some data out of S3, instead of downloading the whole file, the whole object, and then parsing it in memory and filtering, you can do all of that by using Amazon S3 Select, for example. So you really fetch only the data that you need from S3. And so you minimize network latency, and you delegate all the processing to S3. So you use your function only to transform and manipulate and maybe store somewhere else that data, and not to transport a lot of bytes over the network. Another idea, this is very powerful, is try to discard the events that you don't care about as early as possible. You can do a lot of that in the trigger configuration. So if there are S3 or SNS events that you don't care about, like if all you want to do is for every new JPEG uploaded to S3, JPEG file, an image uploaded to S3, trigger this Lambda function, you don't need to filter the JPEG extension inside the Lambda function in your Lambda handler. You can filter out all the non-JPEG objects directly in the S3 trigger, and that's super easy to do. So every invocation that doesn't happen is money you're saving. So you better avoid those invocations in the first place. Another thing you can do is fine-tuning your resource allocation. Here we're talking about memory, but keep in mind that by tuning memory, you're actually tuning power, because with more memory comes more CPU, more networking, more I/O, and everything else. Lambda destinations, it's on this list because So destinations allows you to take the output of a Lambda function for asynchronous invocations and chain it or pass it to another destination. It could be another Lambda function, or it could be an SNS topic, an SQSQ, event bridge, and so on. Now, why is it a way to optimize for cost and performance? Well, because simply, if you think about it, how long does it take to publish an SNS message on an SNS topic? It might take 10 milliseconds, 20, 30 milliseconds. Well, if you do that with destinations, you don't have, first of all, you don't have to write the business logic to do it. So you can spare, I don't know, 10 lines of JavaScript or 10 lines of Python. But most importantly, you're not paying for the execution time to go and write into SNS or SQS or even Bridge, because that operation will be done by Lambda, the service, not by your Lambda function. So you might be able to shave off another 10, 20, 30 milliseconds of your execution time. So the function still needs the IAM permission to go and write into SNS, but you don't need to write the code and to pay for the execution time. Last reminder on this list, keep in mind retry policies, because they are not free. So every time an asynchronous invocation fails, that function is invoked again twice. You can now configure that. You can say try only once or try 0 times, no retries at all. So you can configure that. So if you don't need it, set it to 0, set it to 1. If you know that you need it, and it's often very, very useful, keep in mind they're not free. So just keep that in mind. Now, there is one thing on this list that does not force you to re-architect anything. You can do it without changing any line of code, without changing anything in your architecture. And for a few minutes, I want to focus on that, because I think it's super important and it's super useful if you understand how it works and how you can actually leverage it for optimizing. And that's resource allocation. Now, I already mentioned that when you tune the memory, the RAM of your functions, you're actually allocating more power, more or less power. Now, this is super important. So from now on, I'm just going to say power every time I mean memory. I don't know why we called it memory. So keep in mind, if your function doesn't need a lot of memory, a lot of developers will just give it 128 megabytes, which is the bare minimum, thinking that it will be also the cheapest. But is it true? It's not true. So we'll get there. I'll show you. I'll demonstrate it to you. So let's look at an example with actual numbers. Let's imagine that all my function is doing is computing all the prime numbers up to 1 million about 1,000 times. Not very useful workload, but it's an example. So most developers I know will just say, yeah, I don't care about the speed of this or the performance of this. It can be done asynchronously. Just give it the cheapest option, 128 megabytes. So with the cheapest, not really cheapest, with the lowest power option, you're running for about 11 seconds, and that's the cost per execution on average. If you double the power, the memory, you run in 6 seconds, and you are paying a little bit more. If you keep doubling down the power, what happens at about 1 gigabyte is that, hey, we are 10 times faster. And we are paying almost the same. I mean, plus minus $0.00001. So can you afford $0.00001 to be 10 times faster? And now this is a provocation. I just want to be provoking here, but there are cases where that number might actually be lower. So it's just a no-brainer. You just want to use 1 gigabyte of RAM power instead of 128 megabytes. Let me show you the same kind of example, similar visually. This is super important and I think much easier to understand. Now we'll see some of these charts in the rest of the presentation. So let me explain to you what you will find and how they work. So you will find two different dimensions, time and cost, so performance and cost. The red line is always execution time. As you can see, the more power we give, so on the x-axis we have power, memory, the execution time goes down, and that's because we are running faster. The blue line is cost. So what we expect in theory is that if we give it more power, the blue line should also go up, right? So what actually happens, and this is a similar CPU-bound example, is that as we give it more power, the average cost per execution is going down. Now, this is mind-blowing for a lot of people. It was mind-blowing for me, so I'll give you another 3 seconds to have a look at the chart, get comfortable with the numbers and with the scale and everything. And then we'll dive deeper into some of the other use cases and how this chart was generated and how can you do the same for your own functions. Take a breath. Ready? OK, go. So before we do that, actually, I want to give you another concept that I find very interesting, this idea of cost-aware performance optimization. Because what happens in organization is that you do not have infinite resources. You have maybe 10, 20, 50, 100 Lambda functions in your architecture. And at some point, someone will come to you and say, hey, I want to optimize my functions. How do I do that? Where do I start? Well, let's simplify, and let's say that you have two functions, A and B. Let's say that function A runs on average for 310 milliseconds. So that means you are paying on average 400 milliseconds, because you pay based on the next 100 millisecond interval. Function B runs for 480 milliseconds on average, so you pay for 500. Now, we do a very quick analysis, looking at the code, looking at historical data, looking at whatever we have. And we realize that function A, I can optimize the performance about 5%. Function B, I can optimize much more, about 15%. Now, I cannot see you right now, but I would encourage you to think about it yourself. Which one would you go and optimize? Usually, I do a raise of hand. So raise your hand if it's A, raise your hand if it's B. Now, it's very subjective, and it depends on your goal. If your goal is optimizing for performance and user experience, probably B is a better option. But if we are optimizing for cost, and that's the mission of this operation here, let's look at the numbers. So if I do that with function A, I am now running, so I optimize 5%, I'm now running at 294, which means I'm paying 300 milliseconds on average. So I've optimized for cost about 25%. If I do the same with B, I am now 72 milliseconds faster. So that's a great user experience improvement. But if you look at the cost, we have optimized 0. So keep this in mind. Of course, you want to optimize everything in the ideal case. But if we have to choose, keep in mind, is it a latency-sensitive application? Does it impact the user experience, the perceived performance of the system? And you can go and decide which one is more worth optimizing. So what's your priority list? Now, I was very fascinated by these problems. I love numbers. I'm kind of a math geek myself. So I wanted to find a way to automate this problem, to find a data-driven approach to find the best optimal power configuration for my functions. And what happened, it was 2017. I was still an AWS customer, and I was working all day optimizing my Lambda functions. Lambda was still very young, but super useful already. And so what I did is I was fine-tuning manually and checking the numbers, but then there were cold starts, and I didn't care about cold starts because it's 1% of my invocations. There is a lot of manual work, and I spent maybe a week doing that. I was frustrated, I was tired. So I thought, can I automate this? Can I build a tool that will take any Lambda function in input, run it with multiple power configurations, and then come back to me with the optimal results. It's a simple empirical problem. Can I just run it, brute force it, try all the possible combinations, and come back with some data-driven results? Now, what I came up with is a project called AWS Lambda Power Tuning. It evolved a lot in the last 3 years. I'm still maintaining it, but I'm not the only contributor. There are another 6 or 7 people that help me. And I've just published a new version yesterday. Why a new version? Because this is also published as a SAR app in the serverless application repository. So you can literally just deploy it with a click. And it's available on GitHub. It's an open source project. Anyone can contribute. Anyone can open feature requests or issues, or if you have questions, just feel free to drop a message there. So what happens is exactly that. You provide some input. The state machine will do a lot of things, will create versions, aliases, run your functions in parallel or in series, up to you, and then clean everything up, analyze the logs, and give you the optimal memory configuration, power configuration. So this is what you can provide in input. There are many other parameters, and they are all documented, but this is the bare minimum. So you specify your Lambda function. And before I go there, all of this runs in your AWS account. So you take the project either as a SAR application or as a SAM, CloudFormation template, and you deploy it to your account, and then you can use it. It's using step functions under the hood. So it's a state machine, and you can inspect it visually and so on. So you provide your Lambda function, the ARN of your function. You can specify at runtime which power configurations, which power values you want to test. There are more than 46 of those values. So not only these 4, 5, or 6 that we can remember easily. Then you specify how many times you want to run each power configuration in parallel. 100 is a good number. The minimum is 5 or 10. I recommend at least 50 or 100, so you get statistically relevant data out. And you can also specify the payload, and then there are a few more parameters. If you want to run it in parallel, in series, if you want to automatically set the optimal value at the end of the execution, if you want to have weighted payloads, if you want to optimize for cost or performance, or some weighted balanced weight in between. So there are a lot of customization parameters. I'm not going to dive deeper on that, but feel free to check out the documentation. What you get as output of the state machine execution is this. So you get some results. You get the optimal power based on the optimization strategy that you have chosen. You get the average cost and the average duration corresponding to that power. This is a cost in dollars and duration in milliseconds. And then you also get some metadata about the state machine execution itself. So you get how much you paid for the state machine, the step function, and how much you paid for the Lambda execution. So this thing is running in your account, so it's not free, but it's very affordable. So unless you choose a huge number for the number of executions, and unless you test 20 or 30 or 50 different power values, if you test 4 or 5 with 100 executions, you are usually below 1/10 of a cent of a dollar. It's very cheap, very affordable. So there are even customers that are running this as part of their continuous integration. So every time they want to deploy a function, they just power tune it automatically and go with the production deployment. Then you also get a visualization URL. And this is super important because that's exactly what I showed you before. You get a dynamic browser-based client-side rendering visualization of the numbers, because it's much, much, much easier for us as humans to look at these charts than to look at the numbers in a log stream, at least for me. If you prefer logs, check the logs. So just a clarification about this tool, this visualization. So it's based on a static website that I own. So it's completely free to use because it's just a very cheap static website. And most importantly, it doesn't store or receive any data about your function, your ARNs. All the processing, all the rendering is done client side on your browser in your machine. So there is no way for me to track any numbers or any account or anything else. So, and if you still don't like it, if you still don't want to use it for free, you can customize the URL. And so you can build your own visualization tool and do whatever you want with it. Now, I had a demo, but maybe we are a bit late for that. No, let's actually do it. Cool. So I hope you can still see my screen. Let me, yeah. So this is the project, and you can find it on GitHub. The easiest, super easiest way to deploy this is how to deploy the state machine with SAR. So you just click on SAR, this link here. So you are shown this SAR page. You see how many people deployed it across different regions. So if I click deploy, here is what happens. Okay, I'm in Ireland, all good. So you're given a review page where you can check out the template, the permissions, it's all these privileges, and you can customize the name of the application. So I'll do user group demo. And I can customize the default power values. I can customize the IAM policy. In this case, this state machine will be able to run every function in any region. If you want to shrink it down to only specific regions or specific functions, you can customize it at deploy time. And you can customize other things. I acknowledge, and I want to deploy. Okay, now it will take about a minute to deploy the whole thing. There are 3 or 4 Lambda functions. If you're curious about the internals, these are the functions: initializer, executor, cleaner, analyzer, and optimizer. If you're curious about the internals in the documentation, here is all the inputs you can have. Here is how to use in CI/CD pipelines, how to do weighted payloads, how to have post-processing functions for fine-tuning functions with side effects like create or delete from a database, for example. Everything's documented. You also have some internals. So if you want to know more about the individual functions, you can go there. And here we go. We are good to go. We have deployed the whole thing. Now I can go to step functions. And this is the state machine we have just deployed. As you can see, the definition is the same and nothing's happening. I have to execute the state machine. Now, the input will look like this. So let's go and copy and paste it. This is the default input. I can also give my execution a name, demo execution. I will need an ARN of a Lambda function. So let's go to the Lambda console. So I can pick one function to optimize. So I have a Lambda function that is computing all the prime numbers, the same function I was talking about. So let me copy the ARN. It's not doing anything magical. It's only doing, from 1 to 1,000, compute all the prime numbers up to 1,000,000 and print the results. Nothing magical. So I'm going back to step functions, paste the ARN. I'm okay with testing these. Maybe let's get rid of 128 because it will be very slow, like 1 minute execution. I want to run it maybe 30 times. Payload doesn't matter. Parallel invocation is true because it will be much, much faster if you don't have problems with the original max concurrency and I want to optimize for cost. I'm totally okay with cost here. So I just start. Let's see what happens. So now it's initializing everything. It's creating aliases and versions so that everything can be run in parallel. In this second step, the executor. So the executor, as it's a map state, so it's now running 1, 2, 3, 4, 5 different concurrent branches. Each branch is testing one power configuration. Done. Cleaner, analyzer, and optimizer are super quick. So the output is this. So the optimal configuration for this function is 1 GB. And what happens is I can now take the visualization URL, just paste it in my browser, and very, very easily visualize the numbers. So it's not going to be exactly the same everywhere. It depends on the region. It depends on a lot of different factors. But you know what's the cheapest, the most expensive, the fastest, or the slowest, right? And here, well, I'll probably go for 1,000 megabytes, so for 1 GB of RAM. If performance is more important for me, maybe I still want to go for 2 GB. And now what I would do here is actually testing the interval between 1 GB and 2 GB. So maybe here in between, I might find more optimal results. Now, let me go back to the slide so I can actually show you some other charts about not only CPU bound workloads. So, for example, let me tell you about some of the other patterns. First pattern I want to tell you about is what I call the no op. So all those functions that don't do very much, they don't do any API call, they don't do any long-running computation. All they're doing is maybe getting an event as input, manipulating it a little bit, checking a parameter, storing something in memory, or not even that, or maybe just returning a simple string or a simple OK. So usually you don't have any API calls or anything else. Now, why are these kind of workloads important? Because there are many of those. Every time you integrate with another service, if you don't need to go and store data somewhere, call a database, call a third-party API, you are in this use case. So here, there is no way to make it cheaper. As you can see, the blue line always goes up. So if I give it more power, I'm not going to get any cheaper than that. I'm already below 100 milliseconds. You can't go any cheaper. On the other hand, the performance might, you might see some impact in the performance. As you can see here, I'm going from about 5 milliseconds to 1.5 milliseconds. Now, it might not be a huge gain. If this was an HTTP API, saving 3 milliseconds is not crazy. But if this was part of a microservices architecture with many different services talking to each other, and you can shave off 5, 6, 10, 15 milliseconds from each component of the architecture, you might end up saving hundreds of milliseconds in the overall user experience. So keep in mind, you may be tempted to just use the 128 memory configuration, but if you just give it a little bit more power, you might end up with better performance. And don't trust me, just try this with your function and see what happens. Let's go into the CPU bound category. So this is not the same. This is an example where I'm doing metrics manipulation, metrics computation, like creating a big matrix and inverting it, for example. Some kind of, imagine this is a machine learning model or something like that. So what's happening here is that as I give it more power, the cost is going down very quickly. So I go down from 9.5 seconds down to less than 500 milliseconds. So that's a huge, crazy gain. If this was a machine learning model behind an HTTP API, you are improving the user experience like 10x. And it's super fascinating because the cost, the blue line, is almost flat. It's not like the previous prime numbers example where it was actually cheaper, with more power. But here, there is a trade-off as usual. The important part is that it's not a linear increase. If you want to go 10 times faster, you don't have to pay 10 times more. You have to pay maybe 15 or 20% more. Is it worth it? That's your choice. But I think it's super important to be able to visualize this and take a well-informed decision based on the data. This is exactly the same prime numbers example I showed you. So what happened is that the optimal power would be 1.5 gigabytes. But I've only tested 6 power configurations. There are 45 plus different power configuration. Is 1.5 gigabytes the global optimum? So what I could do is maybe look around this interval, maybe from 1 gigabyte to 2 gigabytes, and see if there is a better local optimum value around there. So what I did actually was to run the state machine across all the possible power configurations. And you can do that just by saying all as a string in your input. And this is the output. So as you can see here, the optimal value is actually around 1.8 gigabytes. After that, the costs start to grow a lot, but up to there, it's still cheaper and faster than the previous values. So very, very interesting to be able to increase the granularity and check more power values around there. Let's change category entirely. Let's go towards network bound. Here I'm talking about third-party API calls, meaning all those API calls that you do out of AWS. So I'm not talking about DynamoDB or S3 or SNS. I'm talking third-party APIs that maybe you're fetching data from. Here I was invoking cutfacts API, so something totally random. And as you can see, the execution line, the red line, is flat. So whatever I do as far as power, I have no way to make it a lot faster, right? My power doesn't affect their response time. It's slightly faster because in this case, I was downloading a few kilobytes of data. So you have better I/O and better networking performance. That's why you see a trend that shows that more power is better performance. But as you can see, the cost is a lot higher. So maybe I don't want to go all the way here. Maybe I'm okay with somewhere like 256 because I still get a good performance gain for a pretty affordable cost increase. So again, this is up to you. It depends on what you're doing with the function, if it's customer facing or not, and look at your numbers. These are just patterns that you may experience, similar patterns that you may find yourself. Let's look at AWS API calls. So here I am invoking DynamoDB 3 times in the same Lambda function. And so by increasing the power, I can go from 340 milliseconds down to 160, 150. So I'm still paying the same because I've leveled down in the milliseconds interval. So I have twice as much of the power, but I'm using half the milliseconds, more or less. So the cost is flat here. And if I double the power again, similarly, I am below 100 milliseconds. So I'm still halving the execution time and doubling the power, so the cost is the same. After this, there is actually no way to make it cheaper or to be in the same interval because the performance, the execution time cannot go any lower, below 100 milliseconds, you're kind of done. So it's super interesting to have a visual understanding on where is the sweet spot and what's the optimal value for each specific function. Also keep in mind, there is no spatial meaning in the point where these two lines meet each other. It's just kind of random. So don't just look at the intersection, look at the meaning of the curves. Let's look at another use case. I'm almost done. So downloading a lot of data from S3 is not the typical use case. It's not very recommended, but sometimes you've got to do it. You have to do it. So in this example, I was downloading a lot of data from S3, like a big chunk of 150 megabytes. So if I give it more power, it's going slightly faster, but after some time, not really that much faster. I'm at around 5-second execution here. So I kind of got stuck at 5 seconds. And the execution cost is just going up, because if you're not improving the speed, the performance, the cost can only increase. What I realized when I was preparing this demo, this experiment, this pattern, is that specifically in the S3 example, you can actually change one line of code and completely change the pattern. So what I did is I enabled the multi-threading download option in the SDK. There is literally one option that says use multiple threads equal 10 or 20, and you can say how many threads. So if I change that line of code, everything changes. So here I'm at about 5-second execution, and I'm spending something like 4 zeros and a 5. This is the chart with the multi-threading. So totally different. Now, even the slowest execution is already faster than the fastest execution I had before. So with a lot of power, I can go down to slightly over 1 second. So from 5 seconds to 1 second, I'm five times faster. And I'm more or less at the same cost range. So just change one line of code, enable multi-threading, and the pattern is very different. Why does that happen? That's because after, above 1.5 gigabytes here, you get 2 cores. So the function can actually leverage 2 CPUs, basically 2 virtual CPUs, to download data from S3. So with a multi-threading option and 2 cores, as you can see, after 1.5 gigabytes up to 3 gigabytes, it's much, much faster. So keep these things in mind and visualize them. My tip for you is start playing with this kind of tools. Try to visualize data. Maybe take 2, 3, 4 functions that you know very well, that you have written the code, and start visualizing these patterns. I'm actually playing a game with some friends where they send me their execution results visually. I have no idea what the function is doing, and they want me to guess what the function is doing. Now, after a while, you see, yeah, this is probably an API call or a third-party API call, or this is probably just CPU intensive, or this is a big file download. You can look at the patterns and understand what they mean, and whether it makes sense to optimize your functions or not as well. So that's my take my takeaway for you. Try to think in terms of cost performance patterns. Play with your functions. Try to understand the numbers. Don't just guesstimate or blindly choose a power configuration because you think it's optimal. You can do much better than that. So some other takeaways. Think about what you are optimizing. Is it the cold start? Is it the overall execution time? Think about, do you have time to re-architect the application? Can you just start from the low-hanging fruit of optimizing memory allocation? That's a very good first way to optimize everything without re-architecting. You can use provision concurrency for kind of getting rid of the cold starts if you know where you're going to have a peak. Something I didn't mention is that provision concurrency also integrates with the auto scaling. So you don't have to know exactly how many warm runtimes you need. If you know, that helps. So you have a minimum, and then you are still optimizing a big percentage of the user experience. Keep in mind that memory means power. It's not just RAM. Keep in mind that you can optimize and fine-tune your resource allocation even in an automated fashion. You don't have to do it manually like I did. You can do it as part of your CI/CD in CodeBuild or Travis or whatever you are using for CI/CD. Keep in mind this idea of workload categories and cost performance patterns, because while you're writing the code, you can already imagine what cost performance pattern will my code generate, and is it worth optimizing? Can I change one little line of code to affect the overall pattern? And if you want to visualize these patterns, please go and have a look at the Lambda Power Tuning project. I am maintaining it, but I'm super happy to get your help, your ideas, your feature requests, or your pull request as well. So thank you for staying with me. Thank you for inviting me. And my final call to action is just go and build something cool with the serverless applications. Thank you, everyone.